A very good morning to our esteemed dignitaries, distinguished experts, respected faculty members, and enthusiastic participants. I warmly welcome you all to this future-oriented course organized under the visionary framework of GIAN, that is, the Global Initiative of Academic Networks, envisioned by the Ministry of Education, Government of India. Inspired by this very spirit today, the Department of CSE NIT Jalandhar is inaugurating its 5-day program themed Exploring Scalable Data Analysis and Cutting-Edge Graph Mining. I request the dignitaries to please take their seats. At first, I wish to extend a heartfelt gratitude to our Honorable Director, Professor Vinod Kumar Kanojia, whose inspiring leadership and constant encouragement have been the guiding force behind this initiative. We feel extremely privileged to have with us today Professor Sharma Chakravarti sir, whose distinguished achievements and excellence in the field of computer science truly speak volumes of his expertise and global academic stature. Sir is currently a professor in the Department of Computer Science at University of Texas, Arlington, USA, and has been serving the academic community there since January 2000. He is an ACM Distinguished Scientist and an IEEE Senior Member, which reflects his significant contributions to high-impact research. He is internationally renowned for his pioneering work in stream data processing, semantic and multiple query optimization, active databases, and more recently for addressing scalability challenges in graph mining, social network analysis, and multi-layered graph systems. His leadership is further exemplified by his work with the Rome Air Force Research Laboratory and establishment of an advanced research infrastructure at University of Texas, Arlington, USA. This remarkable academic journey of Professor Chakravarti is inspiring and really heightens our excitement for this 5-day learning rendezvous with him. We are thankful to Professor Rohit Mehra, Dean Research and Consultancy, who chose to grace this occasion for us today. We thank Professor A.L. Sangal, Head of Department of CSE, and Professor Harsh K. Verma, whose academic leadership continues to inspire an enduring culture of innovation in the department. We gratefully acknowledge the tireless efforts of coordinators, Dr. Urvashi and Dr. Rajneesh Rani, who have contributed significantly in successfully organizing this event. The one idea that's gathered us all here is the idea of scalable data analysis and cutting-edge graph mining. It inspires us to see the value when it's said, big data is not about the data. It's about the insights we can draw from it. Clive Humbley, the renowned British mathematician and data scientist, once said, data is the new oil, but like oil, it's valuable only when it's refined. He indeed underscored the urgent need of not merely to collect data, but to refine it through advanced analytical tools and intelligent frameworks. Every click, transaction, interaction, and connection generates data, but raw data alone holds little meaning. It is through scalable data analysis and graph mining that this data is transformed into insight, innovation, and informed decision-making. Scalable data analysis lies at the heart of modern innovation. It empowers systems to process and interpret vast streams of data efficiently and reliably. Landmark initiatives such as Google's MapReduce framework and the Apache Spark ecosystem today exemplify how scalability has redefined analytics across science, industry, and governance. Similarly, Graph mining allows us to uncover hidden relationships, influence patterns, and structural intelligence within complex frameworks that traditional analytics often overlooked. Pioneering systems such as Google's Knowledge Graph and LinkedIn's Economic Graph demonstrate how graph mining transforms interconnected data into powerful engines for search relevance, recommendation system, and strategic decision making. So I hope this sets the context and convinces us all that the next 5 days of exploring these exciting domains under the guidance of Professor Chakravarti will be indeed an impactful and enriching academic experience. Now, before we begin this program, let us embrace a ray of light and a symbol of hope that shall illuminate our path. We shall offer our prayers to Ma Saraswati, the goddess of knowledge and learning. In her honor, we shall proceed with the customary lamp lighting ceremony and pay tribute to the embodiment of wisdom and enlightenment herself. I humbly request the respected dignitaries to kindly come forward and join us in the lighting the ceremonial lamp.
Yes.
Hey. लो करो करो You come here. Please join us.
थोड़ा सा साइड तो प्लीज मैम थोड़ा साइड पे अरे सर प्लीज ना लगे Yes.
Thank you, sir, ma'am. I must mention that we are also honored by the presence of Mr. Tejas Chakravarti and Mr. Vimal Kumar, who is the local GIAN coordinator. I humbly request Professor Harsh K. Verma sir, Dr. Rajneesh Rani and Dr. Urvashi to please extend a floral welcome to our valued expert, Professor Sharma Chakravarti sir.
मैम प्लीज आगे आ जाइए आप भी साथ में ओके यस यस प्लीज
Thank you, sir, ma'am. Now I wish to invite Professor Harsh K. Verma sir to please address the gathering. Sir is a distinguished professor at the Department of CSE and has held key administrative and academic responsibilities like Dean Academics, HOD CSE department, HOD IT department, head of computer center, and many such other roles, whereby he has guided and catalyzed the transformation of these departments into modern engines of academic excellence. I request Sir to please share his thoughts and sentiments on how Department of CSE, NIT Jalandhar, is a front runner in exploring the cutting edge technologies and high impact research. Over to you, sir.
Honorable Professor Sharma Chakravarti ji, Professor Rohit Mehra, Dean Research and Consultancy, coordinators of the program, Dr. Rajneesh and Dr. Urvashi, faculty members of the department, and dear participants. It's a great honor to welcome you all on this inaugural ceremony of the GIAN program, exploring scalable data analysis and cutting edge graph mining. Before we proceed with the program, I would like you to introduce the department, because we have participants from many other institutes. Some of them, they have joined online, because since it is in a hybrid mode, I'll brief about the department first. Department of Computer Science and Engineering was established at Dr. B.R. Ambedkar National Institute of Technology, Jalandhar, in the year 1990, with an initial intake of only 40 students in B.Tech Computer Science. Slowly we progressed, and if you talk about present, department is running 2 B.Tech programs. One is in B.Tech in Computer Science and Engineering with an intake of 158 students, and the other one is B.Tech in Data Science and Engineering with 60 students. Department is also running 3 master's programs. One is in Computer Science and Engineering. Another master program is in Computer Science and Engineering with specialization in information security. And the third one is Data Science, master's program in Data Science and Engineering. Department is also guiding roughly 100 scholars for their research in the PhD program. And department is guiding the students in different areas. And basically, department focuses on the holistic growth of the students to prepare them for intense competitive environment in the ever-changing IT industry. Department is also guiding students in the area of artificial intelligence, blockchain, cloud computing, machine learning, deep learning, image processing, Internet of Things, information security, and scientific computing, and many more such areas. Presently, department is having a faculty strength of 34, and we are trying to provide the best environment learning environment to the students of the department. This GRAM program is one of those initiatives. So I congratulate the coordinators for making this happen in the department. I'm extremely thankful to Professor Sharma Chakravarti for accepting our request, and he has graced the department with his presence, and I hope all the participants will be having fruitful 5 days ahead, and wish you all the best from my side. So thank you all for joining this GIAN program. Thank you very much.
Thank you, sir. We shall now rise for the national anthem. This brings us to the conclusion of the inauguration ceremony. We will be together for the next 5 days and to begin our time with a pleasant note, I warmly invite you all to join us outside for a group photo and then proceed to the ground floor for tea. Outside Enkin for tea. Thank you. Photo will happen here only.
Slide on.
Everyone please join here.
Back side पे खड़े विमल आ Please guys.
बेटा एक काम करना प्लीज टेक द चेयर
Sir, they just
प्लीज कम
Come this side.
Okay. Project will please. Okay. Okay. Yes. Yes, please. Wait. One more. Thank you.
आप कमेटी रूम प्लीज जॉइन फॉर
It's all right. Hi, can you hear me?
Yes.
Hi. Good morning, everyone. I'm happy to be here and I'm very thankful to NIT Jalandhar and Professor Urvashi Bansal for making this happen. This has been going on for almost 2 years. We started in 2023 and now it has materialized 2 years later, and I'm very happy to be here. I was in NIT Jalandhar earlier sometimes, several years ago, and had a very pleasant experience. So today, this is part of the GIAN course from the Government of India, and mainly this is about data analysis and what are the latest trends in graph analysis and scalability. So before I go into the course, I want to explain a little bit about what I think you should get out of this course, what is the focus of this course, and what is the takeaway. So the focus of this course is mainly understanding data, application data, whatever data you have in all its glory, their storage, alternatives, management, querying, generating reports. So today we are sort of drowned in the large amounts of data, and many times we don't know what to do. We want to extract useful, good information, but the trick is, how to do it properly and how to do it effectively and how to make sure what you infer is correct and useful. That's the challenge here. We will also discuss tools and techniques needed for various kinds of data analysis, right from mining, knowledge discovery, and processing of objectives, life cycle. Rather than just think about one algorithm, we want to focus on the entire life cycle. From the data, what I call, sort of cradle to grave philosophy, right from the generation of data to drill down and visualization of data. We'll also do a couple of hands-on workshops or tutorials where we have developed some dashboards, and I'll show you those dashboards. So what is the takeaway for you from this course is gaining confidence in your ability to perform analysis on any kind of data. Today, data comes in very many different shapes and sizes and forms. You have transactional data, you have table-oriented data, you have CSV files, tab-oriented files, we have graphs, we have real-time data as stream data, we have images, we have video, we have all kinds of data. So the question is, how do we infer knowledge from different kinds of data, and what are the different techniques that are useful for that? Ability to choose right models and technique. This is very important. I cannot emphasize better, because when you have a piece of data, in order to do the analysis, first you have to model the data. You need to understand what model is appropriate for what kind of analysis. It is not that you can just go from raw data to inference directly, and that won't work for any large amount of data. So it's very important to understand the steps, whether you want a graph model, whether you want a relational model, whether you want some other kind of model is very important. So that is a decision you have to make depending upon what your end goal is. Confidence in your results that you have applied principled approach for data analysis. This is very important, that you understand the data, you understand what you want, and you apply the right techniques. Why drill down and visualization is important. We'll see this when we use the dashboard. It's not enough to derive some results from the data. How do you understand it? How do you interpret it? How do you visualize it? Many times visualization of data is much more important rather than getting a lot of 100 or 5,000 numbers which are very difficult to interpret. So all of these are extremely important from a data analysis perspective. Now, I also want to make sure that you ask me questions. If you have any questions, please feel free to stop me. I don't want it to be a one-sided presentation. I would like you to participate, so I understand what are your doubts, what are your concerns. I'll be more than happy to answer your questions in the best way I can. So the first lecture is about understanding data and need for scalable techniques. So here we will start from the beginning. So what am I assuming? I'm assuming nothing, because as the audience is mixed, I'm not making any assumptions on what you know, just to make sure that I'm not talking beyond what you know and it is not clear. I do realize that many of you are familiar with computer science and programming language, and that will only make it easier to understand, not difficult. So data collection, we just talk about data, but we don't talk about various aspects of that. Collection is one, storage is another thing, cleaning data is third thing, loading, management, and analysis has to be addressed in the context of computers. Huh?
Because it's streaming live.
Oh, this will be visible, right?
No, sir, actually the pan is on. So the pan is on.
Okay.
So we would need your PPT to broadcast this and
To send it?
Please.
Okay, thank you. Okay, so what I want you to understand in this course is going from data all the way to mining, analysis, and scalability, including different models. Rather than give you bits and pieces of information, I want to take you through the entire journey as to what has been done in the process of data over the years and how we are handling it. So let's take an example. You have a data set and want to discover knowledge that will be useful for your business or enterprise or community or for international relations. So this is the basic issue, right? Whoever has data, irrespective of where it comes from, whether it is biological data, whether it is social science data, whether it is data generated by sensors, the end goal is to discover something that is useful or beneficial from that, because there is a very large amount of data being generated. So your data set may be proprietary. So many of the data sets are proprietary, and people who have that are not willing to generate that. Then you have to deal with privacy issues for the data and other things. So that's a totally different thing that we want to deal with. You may have public data, but still you may have to deal with ethical issues and its usage. So for example, in law and criminal extent, you have to deal with what can be disclosed, what cannot be disclosed, what kind of aggregate analysis you can do, what is meaningful. So that is going to be very important. Then we also have what we call synthetically generated data. So what is synthetically generated data? How many of you are familiar with synthetically generated data? So what is synthetically generated data? Many times it is difficult to find real world data set for the type of analysis you want to do. So in order to overcome that, what we do is we generate data synthetically. And there are a lot of tools that have been developed to generate different kinds of data with different probability distributions or with different characteristics, with different properties. And this is very useful because you can generate much wider kind of data synthetically rather than the real world data you find. Because real world data may or may not contain all the characteristics, all the distributions, but when you want to develop your analysis tools and algorithms, you want to make sure it works across all the characteristics, across all the features. So in order to do that, we usually resort to generating synthetic data. And the other advantage is you can generate very large amount of synthetic data. Whatever size you want, you can generate, whatever configuration you want to generate, whatever properties you want. So we'll see some graph characteristics, so we can generate data with different graph characteristics. So that's very important from an analysis point of view. And of course, you have real world data. If you have real world data, then you want to use it and make sure your analysis equally applicable to real world data. So understanding the various types of data and the limitations or expectations for the data is very important. So how will you go about it? I have tried to categorize it into three categories. If the data is very small, then you can understand the data and infer things manually. This is what we were doing 30, 40 years ago. We were dealing with what we call samples. So you take a random sample of the data in order to keep it very small, and then you can analyze it by using very simple techniques, and then you try to generalize it. So if the data is very small, it's much easier to handle that. Then we have, what if the data is large? If the data is large and cannot be done manually, then you need automated techniques and algorithms to process data with a good response time. This is where all the mining, machine learning, and various other algorithms came into picture in order to deal with large amounts of data. I don't know how many of you are familiar with association rule mining. Is anybody heard of association rule mining? Association rule mining came about in the 90s to analyze what we call market basket data. So for example, your DMart generates lots of point of sales data every day. So similarly in US, Walmart generates lots of data, gigabytes of data per day. From that data, they want to know what items are bought together so that they can do the logistics for replacing the items and stocking the items. So it may depend upon the demographics, it may depend upon the region, it may depend upon various things. So there is large amount of work that has been done in what is called association rule mining. This is one of the mining that has been done, came a little bit later than clustering and classification and traditional forms of doing. So if the data is large, you need this. What if the data is very large? Then in addition to the above, you will need distributed and parallel processing techniques. So this is important to understand. This is what we call scalability. So if you have very large amount of data, you need additional techniques for processing them in parallel. In addition to doing the same algorithms, but many times converting the same algorithms into parallel algorithms is very tricky. It's not straightforward. So we'll see MapReduce. Have you heard of MapReduce? How many of you may be familiar with MapReduce? Okay, that's good. So we'll see MapReduce techniques in this course as to how we can achieve scalability using MapReduce, for example. So again, understanding the size of data and what kind of processing and resources are required is very important. Finally, you may ask, who decides what is large? That's a valid question, right? What is large? Something that is large for one person may not be large for somebody else. So it is mainly depend upon the volume and processing capabilities you have. What is your processing capability? If it takes 10 hours to analyze something, then you have very large amounts of data, you need better response time. So you need to go to scalable techniques for that. So it depends purely upon, and we also call it the quality of service constraints. So quality of service is very important, and we will not be dealing a lot with that in this course, but that is something you should understand. Finally, at the end of the day, what you need to understand is good data models, mining, statistics, machine learning algorithms. Also figure out how to leverage distributed and parallel processing. So this is really very important, even though it may look very fundamental, very simple. This is very important to understand because this determines everything else you are going to do beyond this. Any questions? So the devil is in the detail. Suppose you are given a data set and its description. We also call it metadata, and there are ways of describing the data in terms of metadata. Also, you are assumed to know the application area, which we call domain knowledge. So again, this is very important. If you are just given a data set without any information about the domain from which it comes from, it's extremely difficult to do analysis. If it comes from biological domain, social science domain, you have to have some understanding of what the domain is, what kind of things you want to infer from that domain. For example, in social science data, there is something called Big Five. They want to understand Big Five. If it is a biological domain, they want to understand something else. If it's a graph domain, you want to understand something else. So domain knowledge is also important and useful for data analysis. You cannot do data analysis in the void. You need to understand what kind of data it is. For example, if you are monitoring a bridge or if you are monitoring an infrastructure, you need to know the kind of data that is coming and what you want to monitor. So finally, your boss wants you to figure out how to leverage this data set for the business. It may be in the form of generating more customers, retaining current customers. This is very true in the mobile ISP area. You know, they keep calling you to see whether you are going to switch to a different service provider or whether you are going to be there. They want to make sure you are with them. So this is also can be done through mining and analysis. And if you are analyzing spatial data, climate change, USGS data, then it's a very different ball game altogether. नहीं दिख रही क्यों? So what should we do?
So we can just have a break of 5 minutes and we just copy the presentation over there.
Okay, okay.
Because it is not visible in recordings, won't be accepted over there.
Okay, no problem.
ज्योति पेन ड्राइव दे ये इसमें दिख नहीं रही है एक्सेप्ट ही नहीं होंगी रिकॉर्डिंग ये फिर उधर जानी है ना ये रिकॉर्ड कर रहे हो ना हाँ ये एक्सेप्ट नहीं होंगी इसको करो ठीक पहले
So you was going to put the PowerPoint slides, is that what it is?
Yeah, we are going to put the PowerPoint slide and so that everything is visible in the camera. So
Okay.
they are copying it.
Okay,
Yeah.
okay.
In the background, na, it shows like everything is white.
Oh.
Nothing is written. Yeah, I can show you.
Okay.
Like this.
I mean, it is there, but not very.
Not visible, yeah, properly. Yeah.
So what is the solution for this?
They are doing something.
Huh?
They are doing something.
Okay,
Yeah.
okay.
Hmm? Okay. Should I bring some glass also?
No, that's okay.
Jyoti ma'am. Ma'am. So can we start now? Kar 2 minutes. हाँ कर देंगे लाइट सही नहीं आ रहा इसको कौन सा वेट इसको कौन सा वेट ऐसा
Wait, do?
So
He forgot.
yeah
Oh,
so that is why I accompany him
it was go.
he came earlier here na it's his first time
Yeah, but I don't remember when I came last.
he was doing it and going in the left direction I told him to go to right and like that only.
Okay.
He might have reached by asking someone but
Yeah, he would have asked us.
yeah
Okay.
तभी मैं चली गई थी साथ में
अच्छा.
हो गया?
Okay, so we were talking about application or analyzing data for a particular situation. Here is another one. Is there a booster shot needed for COVID? You know, this question was very relevant a few years ago, and there is something called CDC and FDC in the US, and they are charged with providing data, take input from independent advisors who will do the analysis and take a decision. So these are all experts, but they need all the information or the data to determine what to do and how to do. So again, data analysis, as I'm trying to show, that it's part of a lot of different domains in various ways. So how do you decide? The problem we have is it is possible to analyze data in multiple ways. So the question is, how do you choose? Which one will you choose and why? More importantly, once you do the analysis, you need to validate your results. I emphasize this a lot because I have students who do not fully understand the notion of validation. They think whatever the result you get is correct. And that is not the case most of the times. And how do you justify your validation? At the end of the day, you need to convince your boss that your solution is not only good and will work with high probability. So this is the bottom line. When you take up a job and you do data analysis, it is not for the purpose of academic interest. It is for the purpose of taking some marketing action. And that means a lot of money. If you make the wrong decision, spend a lot of money, no outcome, then you will be in trouble. So I call it, there is this concept of doctors without borders. Similarly, I call it analysts without application boundaries, because you want to be a data analyst, but you don't want to think that I can only do analysis for one particular type of data and I cannot do for other data. You should be able to apply your analytical skills for any kind of data that you come across. Maybe you seek some help from the domain expert in understanding the data, but you should be able to do the analysis. So gone are the days when you could focus on a single topic. Today, problem solving and analysis spans multiple topics and disciplines within CS and outside CS. Hence, you cannot just focus on programming language or operating system or data management. So data analysis uses several techniques: cleaning, choosing meaningful attributes for data analysis. This is very important because many times your data contains large number of attributes. Not all of them are useful, not all of them are meaningful. Trying to analyze the entire data set is waste, and it takes more time, and it's computationally more expensive. So you need to figure out which columns or which attributes are useful, which are not useful, which are dependent upon one another, so that you can reduce the number of columns. Mining machine. Hence, do not become a person with a hammer looking at everything as a nail. So if you have a hammer, you tend to think that everything is a nail, so I can hammer it. That should not be your attitude in data analysis. So instead, become a person who can match the right tool for the specific problem at hand. This requires a broader and flexible toolbox. This is very important. So think of it as a car mechanic. A car mechanic has a lot of different tools. It's not just one particular tool he uses. It depends upon what part of the car he's working on, what make of the car he's working on, what model of the car he's working on. This is also very similar to that. You cannot just apply the same technique to every data that you get. You have to determine which technique is appropriate, which technique is meaningful, and why. So, a word of caution. So many times we are in a hurry to fit a theory to the results you see. Make sure your results conform to the conjecture or proposal you have. There must be consistency between theory and experimental results. So this is what I see with my students. I see my students explaining the results even if it does not make sense. Just because they wrote a program, just because they got a result, they think it's correct. And then they try to explain the result rather than whether the result is correct with respect to the theory, whether with respect to the analysis. So there is a difference between analyzing a problem and having an idea of what you should get versus just relying upon what if your program is wrong? What if there is a mistake in your program? And that happens many times because they have not analyzed the problem and have no idea what to expect. Many programming mistakes are discovered after they are explained. Hence, this is very important. You need to have two independent ways of validation. One of them may be theoretical or analytical, the other one is experimental. These two should be done independently and they should match. You cannot just rely only on experimental results. You cannot rely only on theoretical results. Even with ChatGPT, for example, there is this problem of hallucinations. Have you heard of the problem of hallucinations? ChatGPT many times gives wrong answers. Now, if you cannot differentiate when it is wrong, when it is not wrong, you will just blindly take all the answers it gives as correct and then follow them. So that is going to be a mistake. That is also true here. That's why you need two or more independent approaches for validation. Always do sanity check. Always make sure your test data includes boundary cases, not just normal cases. These are the things that you have to be very careful about when you analyze data, because getting wrong results in certain domains is going to be extremely expensive and sometimes devastating and catastrophic. So you don't want to do those kinds of mistakes. So some clarifications, because a lot of times when I talk about data analysis, people ask me, why do I need to learn programming for doing analysis? I can do analysis, but why do I need programming? Although you may be using packages for many tasks which you do, you may have to use appropriate data structures and populate them properly with data. If you are using Python, if you are using RStudio, or if you are using scikit-learn, any of the packages that comes, then you need to understand what a table is, whether the data is input into a table format or a different kind of format, and then how to present it. So you need some understanding of data structures, you need some understanding of what kind of packages, what are their capabilities, what are their limitations in order to use it. So it's not enough just to keep using packages after packages, but need to understand the thing. So choosing appropriate algorithms for what you do is important. Figuring out plotting and visualization options, generating good understandable. So that is one question. Second question that is asked is, does the data sets used for learning matter? When we teach courses, we use one or two sample data sets, representative data sets. But when you go out, you may encounter data sets from very different domains, very different things. So the question that is asked is, I learned on these two data sets, is it good enough? That's a question. So the answer is yes and no, because understand the analysis part. Analysis part typically does not change. Data may change, but the analysis part does not change. No matter what the data is. You will be encountering different and complex data sets all the time. Representativeness of the data set is very important. I have highlighted it because if the data is not representative, if the data is skewed, or if the data is biased, so there is a lot of work going on in today saying that a lot of things AI and ChatGPT are generating are based upon biased data. So just to give an example, in the US, we have different populations. We have a white population, Hispanic population, and African population. Now, if you take a data set that is predominantly white, then it is going to give results in a biased manner, or predominantly African American. So data set is very important. Or take male and female. So today in many medical data sets, there is less percentage of female data set, and that gives biased results. So it's very important to understand the data set, make sure it is representative, balanced, and there is no bias introduced due to the data set. The algorithm is the same, but the data set can introduce bias. Do not get hung up on the latest packages. Process or analysis does not change. Pre-processing is very important. How will you cover all application scenarios we are going to encounter in our career? We cannot, but importantly, we do not have to, because as I said, the process of analysis will remain the same. Details will vary, so please focus on learning the analysis, not on the data sets. Please focus on visualization and presentation. Focus on sanity check and validation. These are more important than just focusing on the data set. What about different types of pre-processing? Same as above, may have to add more tools to your pre-processing batch. At the end of the day, domain knowledge coupled with robust analysis techniques are what is important to be a successful data analyst. So this is extremely important. I cannot overemphasize this. A lot of times this is lost or missed. People are very eager to just do the analysis and not think about what they are getting out of it, whether it is correct or not. So, is the problem of data analysis new? What do you think? Obviously it is not. So, here is a slide from 1982. Nesbitt said, "We are drowning in information but starved for knowledge. This level of information is clearly impossible to handle by present means. Uncontrolled and unorganized information is no longer a resource in the information society. Instead, it becomes an impediment." We are saying the same thing after 40 plus years. Every sentence is true. We are still drowning in data. We still do not fully know how to infer knowledge, and data by itself is not enough. What is important, a lot of industries think they are sitting on gold mine, which is their data, but they don't know how to process it. So it is useless. The gold mine on which they are sitting is useless if you cannot get something meaningful out of it. So it is not enough to store, organize, and manage information, which we have done, but it is critical to extract relevant knowledge and make it available for decision making in a timely manner. So this is still, after 40 years, this is still the essence of data analysis. Then the resources were very meager, computers were not powerful, so then the amount of data they had was very large. Now we have very powerful resources, but we have 100 times, 1,000 times the data. So things have not changed very much. So let's understand a little bit about data, information, and knowledge. So this is also a pyramid that was put forth earlier in the 1980s. What it says is, we have very large amount of data. We try to convert into smaller amount of information, and then still smaller amount of knowledge, and finally, if we can, into wisdom, what we call wisdom. So this is a pyramid which takes very large amounts of data and reduces it to, nuggets of knowledge or nuggets of wisdom. Now this can also be shown as the following. On the x-axis we have understanding, on the y-axis we have connectedness. So we can cast this into, we start from data and we add some relationships to data to understand it as information, and then we mine or extract patterns to make it knowledge, and then we want to extract principles to make it wisdom. Now even today, even AI, what we have, is not able to generate wisdom. Wisdom, we have from a long period of time based upon a lot of information that has been assimilated. So there are nuggets of wisdom, but can you do that with the different types of data is still an open question. So data to information to knowledge to decision and action is the process of data analysis. Casting this problem in as a data processing problem, so we have raw data, and what we want to get is knowledge, if not wisdom. And out of that we want actionable knowledge. That means you can apply this knowledge in some way to do something, to produce something, to make a marketing decision, to do some kind of a campaign, whatever it is. And in order to do that, this is the process we use. So the inverted triangle represents the reduction of data from a very large volume to small number of knowledge and wisdom and inferences. And here you can use any technique, any principle, any algorithm, and we have a large number of them. So that is what we need to focus on, how to go from raw data to knowledge, if not wisdom. And that is the whole process of data analysis. So let's look at, so what is data or raw data? You can define a raw data or base data as a value and maybe a type. So for example, if I just give you 480,000, Einstein, male, 3.14, these are pieces of data. It may be difficult to understand this data by itself because we don't know where it came from. But if I give you some more, a data by itself is difficult to understand. That's where you need, there is something called the FAIR principles. We will not go into that metadata, but let us take information. So if you add some context to this information, then it becomes much more clearer, much more meaningful. For example, 480,000 is the number of deaths in US from cigarette smoking. 3.14 is the value of pi. Einstein is a scientist. So when you add the context, this is what we also say domain knowledge or domain information, because the raw data by itself may not be meaningful in any way unless you add some context to that, which makes it easier to understand and figure out what kind of analysis is meaningful. So data science is the science which encompasses techniques, approaches, tools, abstractions of going from same thing, raw data to information to knowledge to wisdom. So not at all new, only the size, variety, complexity keeps changing or increasing. Visualization adds additional complexity. So what is the difference between knowledge and wisdom? Since we said, it's much more difficult to derive wisdom as compared to knowledge. Knowledge is knowing facts and information acquired through learning and experience, while wisdom is the ability to use that knowledge effectively, applying good judgment, insight, and understanding to make sound decisions and discern right and wrong, considering wrong. So there is a difference between knowledge and wisdom, and here is an example that is widely used. Knowing tomato is a fruit is knowledge, but not to use it in a fruit salad is the wisdom. So this is an example that is very often given to differentiate between knowledge and wisdom. Any questions or comments? So now we understand a little bit about what is analysis. Why data, understanding data, and different ways in which we want to deal with data is very important. Let us understand the analysis types. So it is can be classified into descriptive, and the second one is prescriptive. So descriptive means a method for quantitatively describing the main features of a collection of data. For this, we use statistical and statistical measures. Descriptive analysis can be applied something like on the census data. For example, you can compute averages, you can compute frequency distributions of earnings, for example, male-female ratios, histograms of different categories. You can compute percentiles, histograms, distributions, uniform, Gaussians. So these are all descriptive analysis of data, and this is very important and very useful. Then there is the prescriptive analysis of data, which essentially means find the best course of action for a given situation. So when you are given the data, this is what we call actionable knowledge. How do you derive actionable knowledge? Not just the description of data. So the first one is more about the understanding of the data. The second one is more about deriving knowledge that can be used for some purpose. Usually this is preceded by descriptive analysis. This is process intensive, analyzes potential decisions and interactions. Sometimes you may have to do in real time. Goal is to prescribe an optimal course of action, and the techniques vary. You may use optimization, you may use simulation, you may use game theoretic approach, you may use decision analysis measures. You should be comfortable with both descriptive analysis and prescriptive analysis in order to be a good data analyst. So here are some examples to illustrate that. Suppose say we have census data. Suppose you want to know the top 5 states with largest increase in population from last census to this census. Now this falls into the descriptive analysis. You want to know, so you can look at the last census data value, this census data value, and easily compute the top 5 states with largest increase in population. You take the increase in population, sort it in some way, and take the top 5. But if you are asked to, if you want to know which state's household income is likely to rise in the next 10 years, how will you do that? You cannot do it with descriptive analysis. So this is what you need to understand. Descriptive analysis will not tell you or give you prediction. This involves prediction. So in order to do prediction, you need additional data and analysis, something like trend analysis and various other things to see that. So these two are different. So one is along the lines of descriptive analysis. The second one is more prescriptive analysis. So you need prescriptive analysis or predictive analysis. You want to explore latest census data in general, you can use both prescriptive and, but the exploration or search space may be very large. You need to have some idea of what you are looking for. Hopefully not a needle in a haystack. Sorry. Okay. So if you want to do, if you want to do data analysis, as I said earlier, you can do it in many different ways. One of them is the manual approach. So what are the pluses or the advantages of the manual approach? So you have an understanding of the problem and the context. Of course, the assumption is the data size is small. You can use intuition, match real-world semantics. You can explain your analysis or reasoning. But the problem is this can be error-prone because you are dealing with numbers and data and you are trying to do it manually, so there is fatigue, error-prone and other things, so this can be. So just to give an example, I don't think most of you were born. NASA Mars Orbiter mishap, where British measures were used instead of US metric system, and the orbiter crashed because of the units metric units versus British units were used, and it was not detected earlier, and part of the mission did not go through correctly because of that. So this can happen. This is a real world example of what can go wrong if you make mistakes in the analysis. Manual approach cannot deal with large amounts of data. Complex computations are difficult or not possible. So manual is still needed in some way. We'll see why. Now, you can also use the automated approach, which is what we are discussing in this course. The positives are it avoids computation errors, assuming your program is correct. As I said, many times you want to make sure your program is correct first, or your package is doing the right thing. You can deal with very large amounts of data. You can analyze in multiple ways, takes less time, but someone has to come up with algorithms. It is not magic, right? Someone has to develop the algorithms or the analysis. Someone has to design, program the system. Someone has to validate the system. Someone has to sanity check before using the results. So these are the things that you need to worry about in automated processing. And the third category is kind of hybrid, human in the loop. This is very much the essence of data science. Humans play a critical role, but a small role. So where do they play the small role? As a domain expert. So you can do the analysis and everything, but the interpretation of the results will involve a human who has a better domain knowledge than somebody else. So you cannot give a mechanical engineering problem to a botany expert. They won't be able to make much out of that. So you need to understand the difference between the domains that you are using. So there are some advantages to manual approach, but today with the amounts of data, we cannot do that. Just to illustrate, I mean, this is something that you are familiar with. I have to do it every semester. So I use this as an example. So for example, take course grading. It can be done with absolute thresholds. I could just tell at the beginning of the semester, greater than 85 is A, greater than 75 is B, so on and so forth. But if someone gets 84.9, should I give that person A or B? That is the question, right? If you just use purely automated one, it will give a B. Whereas if I do it manually, I can take it into account. I can see there is a very small difference, and that difference I know does not make so much difference. So I can tweak it in order to do that. So this is something that is difficult to do in an automated way. So humans can deal with small variations. It can be, so you can also do it using a curve. I usually do it, saying class average plus one standard deviation is A. Again, if someone missed A grade by a very small amount, or I can take into account, for example, so we look for separations for clustering. You can take exception like effort put in, class participation, types of questions asked, active on dashboards. All those things can be taken into account while doing. So there are some advantages to doing some things manually or doing automated, but you can also combine both of them. You can first do it in the automated way and then look at it carefully to see whether you want to make some changes. So that's what you should be thinking about. What if the class average is 82%? If the class average is 82% and the standard deviation is 8, then in my way of doing it, only people with 90 and above will get an A, right? But I mean, everyone is doing very well. Class average is 82% means they're all doing well. So I may want to reduce that. I may use average plus 1/4 standard deviation or half standard deviation, just to make sure, we fairly and consistently evaluate what we are doing. So all of this is part of the analysis and what you do with analysis. So should one give A to 90 and above only? So So data analysis alternatives, advantages of automated approach: fast, can use more data, complex data, can generate reports, can generate plots and visualization, can choose alternatives, easily compare analysis. However, explanation may be difficult. So this is one of the problems we have encountered, and today there is a whole field of research called explainable AI. You might have heard of it. Explainable AI is mainly how do we explain our answers. So when you get your answers from ChatGPT, you don't know how it got their answers. It's a black box. And you just, either you believe it or you don't believe it, but you don't have any explanation as to how the answer was derived. And this is easy in certain models, it is difficult in certain other models. We will see a little bit of that. For example, it's very difficult to explain neural networks. Why you get that for a neural network is extremely difficult to explain. Generalization is also very difficult. So my assertion is, should not blindly assume the output as correct. You need to do sanity check, validation on small sample data. So even if you have large data, take a small sample, preferably a representative sample that you can manually verify. Run it and see what it gives. Make sure it is doing what you expect it to do correctly. And then hopefully you can trust it on the larger data. So data analysis is not as easy as you think. It looks easy because just apply an algorithm and throw the result. I think that it is not what it is. You need to really understand that. So bottom line for data analysis is we want to process large amounts of data. We do have large amounts of data. We want the flexibility to slice and dice data in many ways. We want to do it very fast. We want to do it incrementally. This is another important issue. In mining and in analysis, you have analyzed data up to 2025. Now you get the data for 2026. You don't want to reanalyze the whole data set, right? That is too expensive and too cumbersome. Is it possible to do it incrementally? That means by adding this data and making sure the results are correct for the whole data, not for just this year data. And that's the real challenge. Doing things incrementally is not very easy. We want an efficient approach. Efficient, I mean, we want good performance, we want good speed up, we want scalability. I just added, we also want no liability if something goes wrong. This is what you hear from all the companies. Airlines, you call them and say, this is not our problem, it's a computer problem. Who is designing the algorithms for a computer? Themselves, right? So it's always easy to blame it on the computer. But it is not really the computer that is making the mistake. It is the human who wrote the algorithm or would not understand the decision is making the mistake. So we want to compete others, outcompete. This course is tailored for data scientists to understand the subtleties, issues, and other things. So what tool should we use? So I mentioned this, but today widely used tools are, Python is used. I'm not a very fan of Python for various reasons, but Python is very easy to use, very easy to understand, very easy to program. And also there are tons of packages that come with Python that are tailored for data analysis and various kinds of analysis. So it's a quick and dirty way to do things. Whereas if you want to do the same thing in Java or C++, it takes a much longer time and you have to spend more effort in doing that. So that's, RStudio is very popular for statistical analysis. Pandas is, I don't know how many of you learn or you are taught. There is others, SPSS, MATLAB. The question many times they ask, which one is better and which one should I use? Now there is no single answer. There is no silver bullet. You really need to understand that. It depends upon who you ask and what the needs are. All are useful for basic analysis. So if you are doing more statistical work, RStudio is better because there are more packages and more things implemented in that SPSS. So there is also a learning curve, varies from person to person. So that's also important to understand. It's not the same. Learning Python may be faster than learning RStudio. Learning SPSS and MATLAB may be a little more difficult. So there is a learning curve to learn any of these things, but all of them may be useful for different purposes in different ways. So you cannot say just, I will just learn one thing. You should be willing and prepared to look at alternatives. So, brief history of information. This is for Gen Z perhaps who do not know what this is. So information can be of two types. Till 1946, we were mainly dealing with analog data. So analog data is mainly signals. It's not digital, so when you go and take your EKG, for example, you get an analog output, which is a curve that goes up and down. That's a signal-based curve. But we have sort of transitioned into digital form. And for the digital form, these are my classification. You can think of it, data in the digital form, there was a pre-database management system where data was analyzed without using a DBMS, post-DBMS, and post-internet. If you are interested, there is a book called The Information by this guy. Very interesting reading, but it's very huge. 1,000 pages if you have patience to read. So where did we get the notion of a bit? We understand it today. This was put forward by this guy, Claude Shannon. You might have heard of Claude Shannon of Bell Labs, used the word bit in 1948 as a unit of measurement of information. Today we just say, 5K, 10K, GB, all are bits, right? But there was no notion of bits before he put out the notion of how do we measure information. Okay, there was no way to measure information before, and this came about in a paper. There was no way to measure information before. Introduced the notion of redundancy to correct errors in transformation. So all of you have heard of CRC, cyclic redundancy check. When you send something and when it is received on the other side, how do you know the transmission is correct? In order to test the transmission is correct, you use all this CRC and other codes, and that will tell you whether the transmission is correct. All this came out. Interestingly, in that book, it talks about the notion of error correction was used by drummers in Africa 200 years ago. They have used it for communication from one village to another village. So here is a real question for all of you. We had two transformative events in the last 1,000 years. So two transformative happened in the last 1,000 years that changed our life significantly. And I'm sure all of you are aware of it, but can anyone tell me what was the first event that changed our life in the sense that changed the volume of information, volume of data that we are dealing with, and what was the second information that further intensified the volume of information and the data we are dealing with? Can anyone take a guess? If not, anybody? Take a shot. 50-50, you are either correct or wrong, so you'll be 50% right.
Introduction of social media. After the introduction of
Huh?
after the introduction of social media.
Okay, sorry, I'm not hearing you clearly. Can you?
After the introduction of social media,
That's too recent. Now, I'll come to that. Yeah, social media, true, but the first one was the printing press. So think of a time where manuscripts were generated, copies, by handwriting. So people were copying books by writing. So, Bible was written 200 times to make 200 copies. So everything was manual till the printing press came about in 1454. And look at this. From 0 to number of copies, this is 1 trillion within a short period of time. Duplication and amount of volume of data increased significantly because of the printing press. This was way before anything else. Before that, copies were made by writing in hand. So just imagine how difficult it would have been. So this is the first event which happened 800 years ago. So what is the second event? Internet. So here again you can look at the volume of data going into zettabytes. 1 zettabyte is 1 teragigabyte, and this is the expectation of the increase in the volume of data. So these two events changed everything in terms of the amount of information you are going to deal with. And that brought new challenges, new things that we had to do. You could not just process information in the same way. So other enablers, inexpensive sensors, they were one of the things that generated 24/7 data, which was not there. Mobile devices. Today we take images and video left and right. We don't care about it. But nobody sees it after you take it. It just stays on your storage. The storage makers are very happy that you keep taking it and buying more storage from them. Advances in storage technologies. However, this is the key. Analysis, information fusion, filtering of data has lagged significantly. So generating data is easy. Analyzing and understanding data is very difficult. That is the main problem. You can generate lots of data, but then what do you do with that? Okay, so what? These events that came about due to technological advances also meant that it is not enough to create volumes of data. What can we do with this amount of information? NASA has warehouses with tapes, computer tapes. You might not have seen a computer tape, but we use computer tapes for storing data because they are very cheap and you can put a lot of data on that. They have warehouses full of computer tapes sitting with satellite data. Scientists can download that data and do whatever analysis they want to do. So a lot of that is being done. So every satellite that goes up generates volumes and volumes of data. It has to be stored somewhere, but storage is one thing, then it has to be analyzed for something. If you have heard of Hadron Collider in Switzerland, this is the one where you smash atomic particles. That generates, I think, 1 terabyte of data each day. And then it has to be analyzed and processed. So if you remember, not too long ago, they discovered what is known as the God particle. It came in newspapers. I don't know whether you, something called the God particle. That came out from the analysis of the Hadron Collider data. there was some thinking about the God particle, but they had no evidence for that. But this analysis gave rise to the God particle. So you can Google God particle and you will see, get a lot of information on that. Geological survey, how can it be put to different purposes in different domains? Now the burden of storing, processing, all of them is on the people who do the analysis. This is a major challenge for data center. Ignorance is bliss. Most of you may not have seen a mainframe. How many of you have seen a mainframe computer? Nobody. I'm so surprised. Let alone what a computer looked like before mainframe. A lot of people today grow up with a powerful computer in their pocket. What you have in pocket is more powerful than the supercomputer we had 25 years ago. More powerful than the supercomputer. For them, it is very difficult to imagine a world where one had to go to a computer center, submit a job, wait for a day or two to get the results. Imagine the patients required a single syntax error correction takes 1 day. I remember the first IBM computer in India came to Indians of Science in 1972 when I was a student there. And they had a computer center, they built a new building, air conditioning and all that, very fancy, and we were using card decks. So you type your program, punch your program on a card deck, go and submit there today, then you go back tomorrow to pick up the printout. If there is one syntax error, it's gone. You have to correct it and give it again, wait for next day. This was the cycle time for running computer programs. Just imagine how it would have been to do anything in that environment. Indeed, we have come a long way in a very short, let us understand. So here are some, I put this mainly for you guys. This is a computer called Minsk series, this is a Russian computer, before the mainframe. Imagine the memory it had was 4K, not 4 GB, not 8 GB, 4K. I hope you understand what K is, kilobytes. Not megabytes, not gigabyte. And could program through console, so you could program through the console. It used Nixie tubes and vacuum tubes. I don't think you have even heard of what a vacuum tube is. That's a precursor to diodes and the printed circuits and digital circuits. Here is another early computer using printed circuits. It used to occupy this room, bigger than this room, and it has to be cooled. Here is the famous IBM 360. This was one of the first mainframes produced by IBM, and some of them are still being used today, So and you can take a look at the disk drive. This is the disk drive, commercial disk drive with 5 megabytes capacity. This whole thing is 5 megabytes. Today, what is in your pocket is 256 gigabytes. So think of it, what you have is 10,000 times bigger than that. So this had integrated circuits, 512K memory, multiple disk platters, lots of magnetic tapes, card readers and printers. So today, a 250 GB micro SD card measures 5 by 8 by 3 by 8 and weighs about 2 grams. Costs about, it's less than $24. This was the disk that was being used with the IBM 370. These are the tape drives I was mentioning. They're like huge refrigerators. you mount the tapes. You mount the tapes here, data is stored on the tapes, and you read it through your program just like you read a file, and then process it. This is the early disk drive. This is like a washer. Capacity 50 megabytes, about the size of a washing machine. This is a Russian computer equivalent of IBM 360. In IIT Bombay, we got one of these machines. I ended up working on this machine. We could write assembly programs and Fortran programs in those days. So in a span of 70 years, we have come a long way. We have computers in all shapes and sizes. We have server farms with 10,000 plus machines. You can even program your dimmer switch, rollable LEDs, Google Glasses, VR systems, embedded systems, and it's improving each day. So think of, ChatGPT is evolutionary. Think of LLMs. So I think this may be the last slide for this one. So I'm going to show this. So I won't go through all of it because right now we have just entered this part. Whatever I showed you before until now is around 1970. And we have made progress all the way to big data analysis and big data science. And I feel that a little bit of understanding of what has come about is useful to put things in a perspective, put things in a context. Otherwise, there's a tendency to take things for granted. Oops. Okay, so this is the end of the first lecture. So we are going to take a 5-minute break and then come back for the second one. I assume you are able to hear me. Okay, so let's continue with where we were. So we were talking about mainly data and what is data, what is this one. So okay, in this lecture we will explore data management, and we may not get to the differences between traditional and graph mining, but we will look at the data management landscape, how we have been doing it and how we are going about it. Okay, so the basic thing is we need to bring together data and computation. So that is the sort of the essence of data analysis. So we have discussed data, events that gave rise to increase in data. Independently, we have understood the need for transforming collected data into information, knowledge, and wisdom. We have looked at the progress of computers and computation. We must bring these two together in a synergistic manner to accomplish our goals. And the goals are data analysis is one aspect of larger scheme of things. need software as well as data management techniques to understand the transformation result. Visualization is good. So let us look at these things. So between file systems and today, there have been a lot of new technologies that have come about. We will not be discussing all of them. So we'll discuss how we were dealing with data using a file-based system, and we'll look at why we developed database management systems, and then we go into data mining, and then go into big data. Not in this lecture, but this is the sequence of things we want to do. So today perhaps we will do in this lecture the first two, and then we'll start with this in the next lecture. So vocabulary. So there are a lot of things that have come about, and mainly because of two things. One is user expectations are increasing. Users want better things, faster things, and more flexibility in analysis. And at the same time, technology is also changing. So these two have to really come together properly in order to make things happen. It is not enough if technology improves. It is not enough if user expectations are increasing, but we need to match them. So that's what happened. So we started with file systems, then we came to database management systems, then we came to data warehousing. You might have heard of these things. Then data mining, stream data analysis, NoSQL databases, cloud computing, big data analytics, data science. We will only look at the ones in the blue. We will not look at the other things. So there has been a lot of progress, and there are various reasons for this progress, both technological and otherwise. So I think from a data analyst point of view, you should also understand the basic. I touched something, and okay, I will not touch it. So basic abstraction is files. I think what is important to understand is this concept has not changed in 70 years. The only mechanism we have to store anything in the disk on a persistent storage is a file. And that has not changed, and it's not likely to change. The format of the files have changed, the size of the files have changed, but still, whether it is for a directory, whether it is for text data, whether it's for video, whether it's for image, whether it's audio, everything is a file. It may be a binary representation, it may be a text representation, it may be XML, it may be JSON, whatever it is. So that's very important to understand. So basic abstraction is for storing information digitally is file system. Very simple, yet very full, has not changed since it all types of information. User decides how to store information in a file, typically as records, fields, values within a record, or structured data, or as binary data. So you are familiar with CSV or comma separated files, comma tab separated files, TSV formats, the application. So what is the problem with file system? So the problem with the file system is whatever format you create for the file, the application needs to know it. Otherwise you cannot do the processing. So let us look at what kind of applications we have. So we can categorize applications into three categories. Computation intensive applications, examples are various things. Here we load all the data into memory and then do the processing. So that's one way of doing things, load everything into memory and do it. The second one is the data intensive applications. Here the assumption is we cannot load all the data into memory. Then how do you do that? So you have to come up mechanisms for loading data partially. And that is what we call staging data. You stage data as needed from disk to memory and process that data in memory. So this is more complex, right? Because you have to decide which data to bring into memory, when, process it, and then write it back, bring the next data, write it and process back. This is what we have been doing because we cannot store all the data in main memory because main memory is too expensive, main memory is too small. The third category is, of course, a combination of these two, which includes computation and data. A LLM is a good example of that, which uses very large amounts of data to generate models and then uses that models. Data mining is an example, drilled out a lot of examples. So where does data analytics fall among these types? Mostly data analytics falls into the third category. You need a lot of computing power. You also cannot hold the entire data in main memory. That's why we have scalability, we have data management techniques to use partial amounts of data and then process as we go. So applications need to be aware of data. This is the most important and difficult part. Representation or format is needed. Makes it difficult to change the format once designed. Enhancement or generation is difficult. If the format is changed, then all applications must change. So this is the real problem. Once you design the file format and the applications use it, you cannot change the file format. Because applications do not know where the record starts, where the record ends, and what are the fields. This was the big problem, and so application management was difficult, labor intensive and prone to errors. Strong coupling or dependency exists between applications. So what is the solution? So making use of data easier, we want to use data in multiple ways. So standards of representation of data and exchange of data, use of metadata to understand the data by humans. Metadata can also be used by application programs. So use of data management system was developed to store and overcome the limitations of the file system. In a DBMS, you don't need to know how the data is stored. You are working on an abstraction, whether it is a relational abstraction, network abstraction, or hierarchical abstraction, it doesn't matter. So you are removed yourself from the dependency, which makes life much simpler. In addition to that, there are a lot of data exchange formats. You might have heard of XML, JSON, and others, and also this notion of interoperability. If you want to do interoperability between systems, then you cannot be dependent on the file format or the data storage. That's very important. So DBMS came about to overcome the problems associated with the files by decoupling the data representation from application software. So this is very important, and this is done by a piece of software which is called the DBMS, or the database management system. So when you write your queries or programs in SQL, you don't know how the data is stored. You don't need to know how the data is stored. You only know that there is a relation by this name, there is a relation by this name, and you want to access that. The relation can be stored in 5 different ways, or it can even change the representation from time to time, but the applications do not change. This is the key. This is a very common practice in computer science, what is called a middleware or a level of indirection. This requires software which can bridge this gap. This is done by providing a higher level of abstraction like relations So a relation was used as an abstraction, mathematical underpinnings, RDBMS was one, other was there. Now we have NoSQL, Neo4j and many applications that are following the same kind of thing. So just to give a very brief introduction, in a DBMS we have levels of abstraction. We have the user views, we have conceptual view or conceptual schema, we have physical schema or physical view, and the data is stored. Still, remember, data is stored as a file. That hasn't changed. But the format of the file need not be known to these levels. Only physical schema knows the format of the file, and it will translate or map that format to whatever abstraction format you want. So this is a big development, or this is a big change in the way you look at data, because now you are free from, now the applications don't have to change. The format of the data can be changed, you can do it in a different way, but applications remain the same. This was a big freedom in terms of how you deal with data. So physical schema describes the data, conceptual schema defines the logical structure like relations, and views are on top of that. So there is a single conceptual schema and physical schema, but you can have many views on top of that. So you can write many views. But just to give an example, in the university database, for example, not everyone can see every piece of information. For example, salary information cannot be seen by many people. Grade information cannot be seen by many people. So there are different pieces of information different groups can see, and that is controlled by different views. View one may be, the director who can see everything, maybe the head of the department who can see limited things, human resources that can see a different set of things. So these views become very important. So just to, I don't know whether you have had a undergraduate DBMS course where you learned these things, but briefly, what is a DBMS? It's a very large integrated collection of data. This integrated is very important. If you have a file system, if you have 4 different files, you have to deal with those files individually. And you have to know the format of the files individually. But in a DBMS, you may have 10 relations, and each relation is stored in a different file in a different way. But you don't need to know about it. So it's an integrated database where the middle layer or the middleware makes sure that the applications get the same view irrespective of how they are stored. I give MyMav is the database used for our UTA registration, all those things. I'm sure you have a similar database that is used for student registration, courses and all those things. All of them are relational databases behind the scenes. We have an Oracle DBMS. Whatever system you use for registration and payment are likely to be a DBMS. So it models a real-world enterprise. In this case, a university or a corporation. You have the notion of an entity. You have the notion of a relationship. A DBMS is nothing but a software package designed to store and manage large amounts. So we have gone from managing individual files to managing large amounts of data in a single way, in an integrated way. So that became very important for the use of data. Why do we use a DBMS? It gives data independence and efficient access. Data independence meaning you don't need to know the format of the underlying data. Reduced application development time, because now you are writing SQL queries which are much easier to write than a program. So you're not writing a program, you're not writing how to extract data from a file, but you're asking for I want this information, all students whose GPA is greater than 3.0. And somebody else is responsible for creating the program for executing that. Uniform data administration in the relational database, concurrent access recovery. So concurrent access is important. This is the example I gave. We have about 3,000 master students in our program. If we don't have concurrent access, what would happen? When they have to register one by one. That means 3,000 students have to stand in line waiting for the previous person to finish. But with concurrent access, all 3,000 students can access the database at the same time. This is very useful and very powerful. You can think of airline reservation, you can think of banking, you can think of many applications where hundreds and thousands of people have to access the same database at the same time. You can't ask them to wait for each other. And DBMS provides such a capability, and this is a complex process. The algorithms are complex, but it has been implemented as part of the DBMS, so it's available to anybody who uses DBMS. So this is a very powerful thing. Same thing is true for recovery. Database guarantees that even if it fails for any reason, power failure, for programming reasons or anything, none of the data will be inconsistent. It can bring it back to the consistent state, so that's a very powerful paradigm. So application development, persistence, scalability, portability, application development time is reduced, information processing was raised to a new level of abstraction. So just to give you how it happened in a small way. So I try to compare. So look at the size of the box here and the size of the box here. That tells you how much work an application has to do. So if you only have a file system, then everything has to be done in the application. You have to model your data. Thank you. Okay. You can model your data in the application. You have to keep track of the semantics. You have to write the program, and you have to use the transaction management. So everything is done by the application and very little by the underlying system. Instead, when you come to a database management system, some of the aspects from the application was pushed into the server. So transaction management and other things were pushed here. This application development cost and time reduced. When you go further, when you develop a relational DBMS, so these are the approximate, then it further reduces, query processing is done, application and modeling. And then we came into object-oriented DBMSs, and that reduced the application further. And then similarly, we continue, and now you can see that almost everything that you are doing in the application has been pushed to the server. So the application has become simpler. So you can focus on your application rather than managing data. Data is managed by somebody else, so you focus on your application and application semantic. This was a very powerful change from file IOs, and this has been around for the last 40-45 years. Today, database management systems is about $5 billion industry. Almost every enterprise, every website has a DBMS behind it. You may not see it, you may not realize it, but there is a DBMS behind it. So now we have non-DBMS applications and so on. So this is to give you some idea about how complex the software is. So you have to write a disk space management software, which manages the disk space. Then there is the buffer management software. Then there is the file access software. Then there is the query optimization software. Because what comes to the system are SQL queries and embedded SQL programs. And the system should be able to process. In addition to that, this module is what deals with concurrency control and transaction management, and this module deals with recovery management. So together, just to give you an idea, Oracle DBMS has more than 1 million lines of C++ code, C++ code. So imagine managing 1 million lines of code and doing extensions, revisions, and updates on that. How complex it can be. So that's what it means. So DBMS software is not small, it's not simple, it's a very complex piece of software. But once you have it, your life becomes much simpler. So this you can think of, you can think of DBMS as a primitive data analysis things, because you can query the database, you can generate reports from the database, you cannot do inferencing from the database, but you can do other things from the database. So you can think of a very primitive data analysis way that started out in the form of a database management system. So DBMS as an enterprise workhorse, DBMSs have worked for over not 3, about 5 decades. It still does behind the scenes, used for payroll, airline reservation, inventory management, financial data management store, now by Amazon, eBay, everyone. They serve well for efficient storage of management of large amounts of data, generating reports. However, expectations kept changing as technology advances. We will discuss more details on it. So today, database systems are very different. You don't see the traditional database system the way it is. What you see now is a web front-end. What you have is a web front-end, and when you fill up forms on the web, whether for registration or whether for getting your bank accounts, they get translated into SQL queries behind the scenes. They extract the data from the database and present it graphically for you. So the GUI-based front end is there, but everything is done by the database at the back end. That's very important to understand. Other ways of databases make life better. So today you can play network games. I don't know how many of you play games on networks. Network gaming is possible mainly because there are very powerful DBMS sitting behind that stores all your information, all the players and all the things that are there, and then they are extracted very fast in real time for showing them. So again, databases are used for this one. Other databases that you may use, So these are some examples. So again, changing requires functionality provided by traditional DB were no longer adequate. So what people wanted to do was what we call exploration. Exploration is different from query. In querying, you ask a query and you get an answer. But in an exploration, you're not sure of what you are doing. You want to explore in different ways, and DBMSs were not able to do that because they were built to answer specific queries, and they are known as exact queries. So exact queries were the ones that DBMSs could handle. So in order to do exploration, you needed a different technique. That's where data mining came into picture, because data mining gave a different way of analyzing data in the form of exploration. So there is a difference between search versus querying. I think I have a slide on that. You wanted to do data analysis in an interactive manner, whereas in a DBMS, There is no interaction. You give a query, you get a result. You give another query, you give another result. So it's mainly pulling information from the system. Functionality provided by AI and related areas were no longer adequate, so business intelligence was needed. Also, interactive usage was becoming increasingly important. Non-technical users want to use easy-to-use system. So just to give an idea, what is the difference between search and query? There is a difference. In fact, there is a difference between searching and querying and what we do with LLMs. I don't think I have a slide on that, but I can explain. So there is a difference between the two. When you interact with a DBMS, you ask a query in a specific language. Even when you search your database, they're translated behind the scenes into query. So the important thing to understand is queries give exact answers. Either you get an answer or you don't get an answer. There is nothing in between. It's a binary thing. Either there is an answer for this query or there is no answer for this query. But search is different. Search was around even before Google made it indispensable. Text search was very popular. Search gives approximate and similar matches. This is the main difference between exact and approximate, exact and similar. This is what you need to understand. When you type a few words into Google, what you get is an approximate answer or a similar answer. Any document that contains those words, whether that document fits your intention or not. So there is a subtle difference between querying and searching that's very important to understand. And so searching gives similar answers. Also we have to understand, Google, however good it is, will not give you fresh answers, meaning it will give you answers based upon the data it has, crawled data. If new data added into the webs, which it has not crawled, you will not get answers based upon that. So it is not always current information. But from the search perspective, you don't mind that. You don't mind information that is not very fresh. But when you go to a bank and ask a query, you don't want an approximate answer. You don't want the bank to say, your account has either $5,000 or $6,000. You don't want that. You want the exact number that you have in your bank. So there is a difference between what you are asking, what is the context, and what information you want. So there are situations where you want exact information. There are situations where you don't mind approximate information. So that is the main difference between these two. So other thing is both querying and search are pull technologies. So what is a pull technology? A pull technology is one where you are pulling information from the system. The information is not given to you automatically. Unless you ask a query, database will not answer. Unless you type something into Google, Google will not answer you. So essentially, pulling information is different from pushing information. Pushing information, example of a pushing information is notification or alerts, where you get alerts from the system without you doing anything, without you asking for that information. So there's a big difference between pull and push technologies. There's a lot of research. We have done a lot of research in push technology, known as active databases, but that is not part of this course. So again, we come to the same slide where we are now dealing with the relational DBMSs. And just to, last time I did not explain what it is. I think it's important. So the first bullet says, without understanding the past, it is very difficult to appreciate the present and plan for the future. That is to some extent true. So you need to know where you have come from. This is what is called provenance. So provenance is very important for certain things, and that is useful. The second one I think is even more important. Technology provides solutions. It does not necessarily solve problems. So This may look like a inconsistent statement, but let me explain. We think as technologists, we solve a problem. We have written an algorithm, it works fine. But what we have done is just providing a solution. Providing a solution is not the same as solving a problem. I'll give you two examples. We know how to grow crops. We have all the technology for agriculture, but we still have not solved the hunger problem. Why is that? Solution is there, but the problem is solved. The reason is solving a problem takes more than technology. It takes social, economic, political, and all kinds of issues that needs to be overcome. Whereas technology is one component and is very independent. Another example, we developed COVID within a very short span of time. So there is a COVID, but COVID is not completely eliminated because a lot of people, nearly 30% of the people in US refuses to take the vaccine. So it is not enough if you come up with a vaccine. Solving the problem is a different issue. For that, you have to change the mindset sometimes. You have to educate people. There is social issues involved, political issues, economic issues. So don't confuse these two. Just because you have a technical solution doesn't mean you have solved the problem. You have a technical solution, that is true. But solving the problem is a different ballgame. That's what I want you to understand as a person who is in the process of developing technology. You can develop great technologies, but it doesn't mean it is going to be used the way you want it to be used. It is going to be adapted the way you want it to be adapted. It is going to be implemented the way you want it to be implemented. That is totally different from that. To summarize, we have gone from file systems to DBMS, to data warehouses, to NoSQL systems, graph databases, to business intelligence systems. We also have what we call data marts and data lakes. Most of these changes are evolutionary, not revolutionary. That means they have happened slowly over a period of time. Nothing that changed something overnight. So it has taken us a couple of decades, a few decades to do that, based on the user needs, expectation that could be supported by technological changes. Emphasis has been on pull technologies versus push technologies. Both search and querying are pull technologies, notifications, alerts are push technologies. So what is important to realize, we will be covering data mining in the next course, next lecture. There was a system developed called DB Miner by IBM, and this mining package worked directly on the DB2 database. DB2 is also an IBM database, and so if you remember, most of the mining is done through packages like we do Python packages, where we have to feed the data to the mining package separately. You have to create the data, you have to put it into the right format, and then run the mining algorithm on top of it. Whether you've done classification, whether you do clustering, whether you do SVM, whatever it is. But what was realized was that most of the data we want to mine is already sitting in a DBMS or a data warehouse. So if you want to mine data from a DBMS or a data warehouse, you have to take that data out, put it into your file, and then run your mining packages on top of that. And that doesn't sound right? That's how we were doing it. So IBM came up with this DB Miner, which would work directly on the database. In other words, you didn't have to remove your data from the database and say, mine the combination of these relations using these attributes. Or data warehouse is a better example because data warehouse collects data from multiple source DBMSs and then you could mine directly on that. Now this was very powerful. At some point, DB Miner was so popular, it was selling like hotcakes. And it was so popular, what IBM decided to do was to give DB2 free with, if you bought a DB Miner system, they would give DB2 for free. It was so popular at that time. So you can imagine the utility of building a mining system on top of a DBMS. So new drivers, business intelligence system became as important. Ability to store multiple years of data online, mass personalization. So personalization came out much later. So today, whether it is healthcare or whether it is something else, personalization is becoming very important. How does one personalize for you, for your characteristics, for your data rather than for aggregates all the data or community other things. So personal healthcare is becoming very important. Personalized inferencing is becoming very important. Identifying new and profitable markets and channels, increase customer loyalty, decrease risk. So this brings me to the end of this one. If you want me to continue a little more, I can start on lecture 3. Depends on what you want to do. I can either stop here or continue a little bit more.
We can continue with the lecture 3 for